micro, nano education for everyone.
All right, so Ozgur is now going to talk about his program at Grand Valley State University, I think it is.
So this is me. You can call me shortly Oz. And so hopefully you can see my cursor as well. So I'm from Grand Valley State University, and Matt touched the experimental part, the hands-on part. Now I'll be touching more about the simulations that we can run. And in the long run, maybe not this year immediately, but we also have a clean room at GVSU too, and we would be very happy to work with you there as well. Okay, so I'll be talking about first a very brief introduction to my research area. I'm a nanophotonics engineer. Myself, even though I'm an electrical engineer, that's could be like a sub portion of the electrical engineering as well. But what is nanophotonics in the first place, or what was nanophotonics? What was photonics before the emergence of the nanophotonics? So you can see here light, white light source, and Newton's famous experiment, the dispersion. So white light source is made out of these different colors, as a lot of us know, I'm sure. And light is a wave phenomena. So I kind of like guide the waves. All of my work is about waves in general sense. So when we talk about the waves, the first thing that comes to students' mind is the ocean waves. And it's very similar, different in the physics, but you see like we have these peak-to-peak separations that we call the wavelength. That's the important term. And light propagates in terms of these kind of waves, and the wavelength phenomena, same kind of happens when it comes to light too. So photonics was in a way, dealing with the transportation of the signals, the data from one point to the other in the form of light, instead of just solely depending on the electronics, which was electrons, right? Currents in the most general sense. So, and I'm sure everyone must have seen this picture before. So we have a lot of wave phenomena happening, like the more familiar stuff to you will be like radio waves, microwaves, infrared, visible. So a lot of the things that I work with are happening inside this infrared visible spectrum. And this is showing you like the wavelength, the scales of how things look like at that portion. All right, so photonics was dealing more about the refraction of light. Again, here, I'm sure a lot of you must have heard this gentleman's name, Snell's law, right? So when light comes to a different refractive index, right? So it kind of refracts. So we will have like total internal reflection, or like we can have refraction going in through the other place. So N1 to the N2, we can go into another medium as well. And we see that the light kind of refracts here, and the spoon is actually continuous, but we see the refraction phenomena happening. So everything was really well known, and you can have like light source coming from the top, and that's what I do. I do a lot of simulations, electromagnetic modeling. That's the fancy way of saying light modeling. So you can have like light coming from the top, and as it propagates inside a different medium, like refractive index of 4 and a thickness of 400 nanometer, okay, at different wavelengths, like 356 and 400 nanometers. These were all well known. So you would have like reflections at the top surface and the transmittance to the other side. So you're basically witnessing the transmission of light through the slab, this nanoscale slab. And you're seeing here the peak value. So as it's propagating, it's a sinusoidal wave we're looking at from the top. So if you look at it from the side, we would still see those wave phenomena like the ocean waves, the peaks, ups and downs, but we're looking from the top and we're seeing the intensity of the light propagating. These were all very well known. That was just yesterday's knowledge. And by utilizing that information, we could like send from one port to the other port, or you can even like think of your own experiences in a fiber optic cable. Like you send your light from, like you have your light source, you send your light from one point, and the light is confined within this region here because of, again, the same Snell's refraction phenomena and the total internal reflection that's happening. That's keeping the light within these bounds, so the light doesn't leak away, we don't lose information, and we get the information at the other side. This was, again, all old news before 1990s, before 2000. So you have your waveguides, as we name them, and you can present your light from here, your information. And this is, by the way, a free simulation tool that we can access over the web. And if you're interested, for example, I like to work with these kind of tools, free tools, right? So that everyone can access. And it's really, you don't really need to know a lot of details about the physics, the science behind it. It's going to take time, but it's more about scripting at that point. So we can discuss, like I can show you the quick and easy ways to script these things to define, for example, this kind of a refractive index distribution where you have a high refractive index in the middle point where you have like less refractive index here. So you see light liking to stick to this high refractive index medium just gets to be guided through this medium. And this is what we call the waveguide. And we have all these things that can easily be happening. So this is not a free software, unfortunately, but you're seeing here a video that I recorded. Like you can send light from one point and then get the light to the other port. So this was all photonics. Again, yesterday's news. And you have like continental connections that are happening. Like even our Ethernet connection is happening over fiber optic cables. So light is extremely important these days. And waveguides are the main way to guide the light, but we can achieve more. So, okay, here we go. Now, nanophotonics. We can, instead of working with just slab mediums or just homogeneous medium, like you can see on the right side that I call bulk medium, you can like create these nanoscale, again, periodic configurations. And this is, again, a simulation. Now you see that the light, as it goes from top to down, it gets to be scattered in a really funny way, right? So we can utilize these things. So you can create these periodic configurations. I hope you can see these little circular configurations. And you can send the light from the bottom, and all of a sudden, this periodic configuration, as you can see, does not allow light transmission from the bottom to the top. So the light doesn't get to be transmitted to the other side. What do? You just tune the light a little bit. What do you tune? The wavelength. You just tune the wavelength a little bit, just like tuning the radio channel. And then all of a sudden, light gets to be traveling inside this periodic configuration. This wasn't explained with Snell's law or the well-known optical phenomena in the previous centuries. This was now the nanophotonics that's coming into the picture. Now, what can you do? You can just work with the same medium that wasn't transmitting before, that we can call like impenetrable forest, but you can just take those things out. Let's say those nano-engineered atoms out. So you just remove those out and you create a defect, and then you can guide the light in that direction, the expected direction. Where's the light gonna go? It's just bound to go in this right direction, right? What happens if I do it for the other way too? So what if I remove these other inclusions, the other atoms here too, these nano-engineered atoms? Right, then we get a beam splitter. So the light will have to choose, and will just pump 50% of its the power there and 50% of the power there. It will not be destroyed, or it will not penetrate into these nano-engineered periodic configurations that we call the impenetrable forest in this case. So it's going to be, again, leaking away if I remove too many, because it's a periodic effect. And it will not be guided in that kind of a good sense when we try to do this with, again, block medium, like the fiber optics, like a homogeneous block, like I was saying, slabs, right? You see there's lots of like leaking, a lot of things are happening. Again, so that's what I do. I am one of the light benders, so if we want to call it that way. And for example, another phenomena that we work on is the refraction of the light. How about negative refraction of the light? This was a structure that I had built during my PhD studies. So you pump the light from the bottom, you build a prism, and this is all simulations again, and you can see that the light gets to be negatively refracted. You can think of it this way. So this is positive refraction on the left-hand side, and we end up with a negative refraction on the right-hand side. So you can see the negative refraction much better in these kind of simulations, right? So this is totally unexpected. So this is completely new phenomena that's coming with the nanophotonics and the nano-engineered structures. very recently, we worked together with Jared and his students, and we looked into the butterflies, a certain type of butterfly. We looked at the nano structures on the butterfly to understand the reflection phenomena, light interaction with the butterfly wing. We looked into the electron images. I'm going to be bombarding you with information. You don't have to keep track of what's really happening in these images, okay? But that's not really the scope. The scope is like getting an idea about what I do and what kind of a plan that I'm proposing here if we work together. So we did simulations and we tried to understand why we have a blue color that's coming out of from this butterfly. The color of this butterfly is blue because when you interact with the blue light, okay, there are these nano inclusions, nanostructures on the wing. It reflects the light back, as you can see here. And when the red light is coming in, red light just goes through the wing, so it doesn't get to be reflected back. So as you can see, as an outcome, we were able to publish this all together with the students. And that's why I'm here too. So I would like to make sure that, we get some output in the end too. So my main goal is to get some publications out there if we work together. And I am hoping that that will be also very useful for your future applications, for your any kind that you may think of, either industry or future academia. A couple of other things that I had been doing was we generated this Nano-lithography tool, an application, again, a simulation tool, to make sure that the technicians or the people who are interested in specifically the lithography will have a very quick way of understanding the basics. So you might go to Matt's clean room and then you will do the hands-on, but how about like we kind of teach you the fundamentals? It's just 1 hour without spending too many chemicals, without spending too much time as well. So that's where the simulations come into play, right? So what is lithography? You can put a structural, a softer polymer on top of what we call a silicon wafer. That's what we start with. Silicon is our breadboard. And you can selectively expose this polymer with light from the top like this. This will alter the chemistry of the polymer. This is a softer material, so you can really, like a sculpturing, you can sculpture this and then remove this with extra chemistry and just you can be left with this structure in the end. All right, so we have, like, for example, this tool. This is MATLAB based, and these are just showing you to get an idea about what we can also create with MATLAB as a user interface together. It's mostly about scripting again. You don't have to know the underlying physics. I would make sure that you will get enough information about that, but the underlying physics is immense, right? So the scope is to make sure you understand the fundamentals and you get an exposure to the, for example, user interface, how to create these user interfaces and how to create these graphs, these nice illustrations. For example, this is an interactive tool. We are exposing this polymer for 25.5 seconds, and then outcome is we get to be removing this portion of the polymer. If we expose it too little, like, I don't know, like 5 seconds only. And if we do this computation again, we're going to find that, okay, so you see, we're not giving enough time for exposure, and then we're not able to sculpture away, etch away enough of that material too. So again, you don't have to understand what's going on, the whole details, but this is kind of what I do. I like to create these kind of learning modules to train the technicians, to train the students for their future jobs, especially when, like Matt was saying, we have this bloom of the jobs available for when you consider this semiconductor industry nowadays. So instead of going into the lab, so this was an undergraduate student working with me, doing the lithography, shaping, patterning the surface. So we have this tool that can give you that access immediately. And these are other students that were working with me in our clean room when I was at Penn State. And several other companies that are listed here that are really looking for technicians, looking for people who will be interested in working in clean rooms. So this is a very recent project that I work on with other undergraduate students, an absorber. So a traditional absorber, like in this kind of aircraft, is to scatter the incoming radar away. So the radar comes in, so you have these geometric configurations that will send the incoming radar in different angles so that the aircraft won't be detected. But how about employing, again, nanophotonics in this kind of design too? And every time I talked about it, I give this example, cloaking, right? So how do we cloak our devices, or how can we effectively absorb the incoming light? So this was like the main idea behind cloaking in the field of science. And we have found that we can effectively guide the light and trick the light, even though the light goes in straight lines. We can alter the space and create a space here that will be hidden. So we can just stretch away the Cartesian coordinate system, and we can hide our materials here. So let me see the output. Okay, so just like a Klingon cloaking device, many of the Star Trek fans will remember, we can send our light from the left and there will be a shadow here. But when we have this nano-engineered clocking device that is surrounding this cylinder here, this is again field simulations, we can completely hide this cylinder in the middle, right in the middle. So likewise, I was working on an absorber that would, again, not allow the aircraft to be, but it doesn't have to be an aircraft, right? So this was just an idea. We were doing these things with nanoparticles, the absorber configuration. So absorber configuration, these nanoparticles that we were working with, you can think of them as little nano antennas. So they capture and resonate with a certain incoming light wavelength. For example, this nanoparticle out of these simulations, we see that it doesn't resonate well with 1.2 micrometers, but it resonates very well with 600 nanometers. What does resonance mean? So it means that it captures the light and it keeps the light, it intensifies the light. So it's like the Tahoma Bridge, right? So that's the same phenomena that's happening here, resonance. The intensity is amplified and the wave is just captured, is confined in there. So this is what we did. We sputter coated, and sputter is just like the contemporary art. You get some, the colors, in this case, it's like gold. You just sputter it on your canvas, in this case, silicon material or glass, and inside the clean room. And you can take a look at it with an atomic force microscope. So this is showing you an atomic force microscopy and how it works. I will turn off the volume here, but I will come to this. That's what I'm showing you this. But there is a tool that's called atomic force microscopy that works with a very small tip, and you can scan over the surface to collect the topography on the surface. So that much of information is enough for us at this point. So the students, when they went to the lab, they sputter coated the gold on a glass material, and then they put it under the atomic force microscopy. They looked at before and after an annealing process. The details, again, are not super important, but as you can see, thermodynamics tells us that there will be a redistribution of gold on the surface, and then we will end up with these little nanodome structures evenly distributed on the surface if the conditions are justified. And we can take a look at these sizes under an electron microscope. We can look at the absorption curves, all of that, of these nanoparticles, different sizes, different shapes. And yeah, so a lot more. And we can understand them with the simulations too. So this was the outcome of the coding that we did together. You can see that the colors are changing. We looked at the absorption, like how much of the light is getting absorbed. And one thing that we did not explore a lot with the student, this is a free simulation tool, and I would like to use it more in the future, like this summer, for example. It calculates for different sizes, like you can put in like 25 nanometers of a sphere gold, or you can make it silver. Let's make it silver. And then you can say mu plot. And this is going to calculate, if you work with a spectrophotometer, this is going to show you, if you didn't, don't worry about the names and stuff, but this is going to show you, this is the wavelength spectrum, which light will be going into resonance, like would we amplify? And as you can see here, that's like close to 350 or so. If this is 400 nanometers, that's the wavelength that is captured by these nanoparticles. I would like to explore this tool more. And I would like to, again, like I was saying, publish if possible with, why not, you guys. So this was a recent conference submission that I did with these students that work with me during this project. But there's more to explore, like I was saying. And just a few more minutes. These are other ongoing projects that I'm working on. I am working on an X-ray characterization method. This is again for educational purposes. X-rays, well, they're like the Röntgen. You break something. Hopefully, you don't break any of your bones. But if the patient breaks the bones, that can be characterized by X-rays, right? Similarly, we can characterize the materials with X-rays too. So there's another, again, a free simulation tool that helps us to understand. For example, what are we looking at? We're looking at copper. Copper has these orbits, right, for electrons. And when you send the X-ray, okay, I won't go into any of the details. The tool's name is, free simulation tool's name is CESA, but it can tell us the exact location of these electrons, okay? And we can make a learning module out of this, like by understanding, deciphering where every one of these peaks are. We can go back and try to understand, okay, where's the electron then in that ladder, the orbital allocation for copper. That's one thing that I'm working on. Another one is quantum mechanics. So everyone is terrified of quantum mechanics, but we don't have to be. So we have an electron that is going to propagate through a potential. Okay, so let me show you instead of talking more about it. So let's say we have an energy of, and this is just showing you like how I do things, just to get you an idea like what I'm talking about. All right, so like these kind of things are the programs that I'm working on, are the things that I would like to continue working on. Okay. The ideas, the science and all that is not important for us. But as you can see, I would like to illustrate. I would like to quickly let the students understand what's going on behind this. In this particular example, we have an electron, which is also another wave, is interacting with a barrier here, okay? It's really a barrier. The electron is expected not to make it to the other side, but it does. It's a very tiny amount, and let's look at it. So you see the Y is 4 times 6 × 10⁻⁶. So that's like super small, 1/1,000th, right? So super small amount, but it still propagates through the barrier. This is kind of like what we call quantum tunneling. This is taught in graduate courses. This is taught in undergrad, more advanced courses of chemistry, of physics. But what if we do it more illustratively, like with these kind of tools, using MATLAB or other graphic illustration tools? We can use some coding experience and we can come up with these kind of outputs. The last thing that I'm going to show very quickly is about atomic force microscopy. We have another place that we can go to, that is Nanohub, and you can just search for it, nanohub.org. And VEDA is a great atomic force microscope. You remember the atomic force microscope I was talking about, the one with its tiny tip? There's a great simulation tool there that's called VEDA. But when I introduced that to my students, I realized that it was a bit too soon, because you can really do advanced research with this tool. So there were some gaps that needed to be filled, and I am working on that. For example, what? So you can see the plot here. The atomic force microscope has a cantilever, and that is gonna be bending while it's interacting. I don't know if you can see my my finger here. It's gonna be going up and down. It's gonna resonate. It's gonna, up to some extent, deflect while it's interacting with the surface. These are what we call modes, these deflection modes that need to be understood. And just as an illustrative example, I would like the students to immediately understand how this kind of a sturdy element can be bent, right, at the nanoscale. And we're seeing here, for example, how it can be bent. Like you can see the red curve here. That's just an example. It's still in the preliminary phase, but I would like to make sure that there is like a user interface, like the ones that I introduced before, that the students can immediately work with and understand what's going on without needing too much math, needing to read a lot of like equations and whatsoever. All right, so that kind of summarizes what I do, what I would like to do in the future. Thanks. All right, so if you have any questions, again, I would be happy to answer.
Hi, Ozgur. That was fantastic. Thank you so much.
Thank you.
And you know, I was looking at the blue morpho work that you did with Jared and some students. And last year we had a blue morpho simulation challenge. Did you hear about that? And did you have a chance to take a look at it?
Yes, I heard about that, but no, I didn't have a chance to look at it, to be honest. Yeah.
I'm just curious whether that might be something that would be of interest in the future. And if you have an alternative way of simulating those. Yeah,
we developed an app that could be used and but we developed a simple app where we could just say, if we put this butterfly into another solution, this butterfly changes its color. So the students could just put in what solution they're referring to, and then they could see, okay, so the butterfly will be like this color as an output of this interaction. So they could understand it without doing any experiment. That's the idea, quick and easy. Hi, I just saw Harold's question here.
The Norton lights?
Yes. Okay, yeah, definitely. That's plasma physics, more related to that. And the outcome is of course, it interacts with the light as well. We see some emissions. So that is not immediately about nanophotonics, but yes, it can be simulated. We are actually kind of doing similar simulations about like the things that Matt was talking about, the tools like the sputtering tool that he was referring to, or other deposition tools that are based on plasma. One of the simulation tools that I work with, like COMSOL, gives me a chance to look at different colors of these plasmas, like the northern lights. Yes, so those can be simulated. Yep. Short answer is yes. And you can do the simulations yourself. So again, I don't want to overwhelm anyone. So the idea is not to understand, and it's impossible, right? You have to get even a PhD to master all this data information, but the idea is to write or present it as a user interface, convert that into a user interface, a simulation tool, again, for learning experience, but also could we also publish this in the future too? That's something that we need to keep in mind, and even like do some fundamental research too. Yes, I see Dominic here. Question?
Hi, Ozgur. Really interesting talk. When you were talking about these nanomaterials you use to direct the path of light without any loss into the material, or if that's not the right word, maybe another word is appropriate. Could you give me an idea of what some of the applications that would be or speculate on that?
Yep, sure. Yeah. At that point, it's when it was first announced, the main idea was to create a great question, perfect lens. So we can negatively refract this light. So can we create a high resolution lens? And still a lot of the discussion is revolving around that. So a perfect lens can resolve anything that would not be limited by what we call diffraction losses. And you can, in theory, you can see like things that you can normally not see with an optical microscope. So without needing an electron microscope, you should be seeing, let's say, like 50 nanometers. That's really hard, even with these advanced confocal microscopes and etc. So nowadays, reaching those kind of limits is super hard. But how can we replace the ordinary lenses? So that was the idea. But then now it turned into really like a lot of different discussions. Like how can we steer the light? How can we use it for 5G, for example, like extrapolate this to microwaves instead of light immediately? There's lots of experiments going on, not just in the optical spectrum, but in the microwaves, radio waves, terahertz, all those ranges as well.